If not, then we go on with the last presentation of this team and last presentation of this day even. And it will be given by Ben Goldby from HR Wallingford. Where it should be on this one.
Oh, okay. Wrong computer.
So perhaps you start.
Okay. Yeah, as Nico said, I'm from HR Wallingford. I work in the flood management group there. I'm also working on the urban flood project, and the work I'm going to talk about today was done in collaboration with TUD, Technical University Delft, so not far from here. Yeah. So the talk today is going to be about reliability analysis, and in particular using computational intelligence methods for improving estimates of fragility and reliability. Okay, so I've just talked through this, but these are the people who worked on this project with us from TUD. Okay, to give a brief overview of the presentation, first of all I'll talk about flood risk analysis models and talk about the specific role of fragility curves. I'll then give a very brief recap on reliability analysis, and I'll go on to talk about a particular problem that was encountered with a complex model that was set up on the New Orleans levee at the 17th Street Canal. And I'll introduce the concepts of meta-modeling and automated searching. Okay, so to give a very brief recap on flood risk analysis models, these are typically the components that are used in developing these models. So we have extreme value distributions that describe the hydraulic loads on the structure. We have the fragility curves, which describe the probability of failure of the structure. That's conditional on the hydraulic load. We have inundation models that simulate the propagation of the floodwater across the floodplain, and then some kind of consequence function, particularly depth damage, but could also be loss of life. These models are used for a range of different purposes, including long-term strategic planning, prioritization of maintenance activities, as well as potential application in emergency planning and management. So the component of these types of models that I'm going to specifically focus on today is this one, which is the fragility curves, which is the probability of failure of the structure conditional on the hydraulic loading conditions. Okay, just to explain a bit about why the fragility curves can be important. If we've got a floodplain area here, we've got a system of flood defenses that's protecting this area. If we imagine this line of defense is loaded to a water level that's below the crest level of the defenses, if we have a breach, we can inundate a particular area, cause some damage or potentially loss of life. Obviously, if we don't have any breaches, we don't get any consequence. So potentially our risk analysis can be quite sensitive to estimates of fragility. And obviously, if we breach in a different location, we can flood a different area, and there may be different types of property infrastructure in the floodplain. And obviously, we can also have combinations of breaches occurring together that can again yield a different outcome, a different consequence. So our estimates of fragility inform the likelihood of where these breaches can potentially occur, and consequently they can be quite influential in determining the risk associated with specific events. Okay, so just to give a very brief overview of reliability analysis, which is what we typically use to derive the fragility curves. We have probability density functions that describe the hydraulic loading conditions. We have probability density functions that describe the structural strength. So in our case, when we're talking about levees, soil properties, things like that. We have the limit state equation, which is a function of the loads and the structural strength. And we have this, what's known as the limit state. So if the loads exceed the strengths, then we have failure. If they don't, we're safe. But if they're equal, we have this Z line, which is known as the limit state. So what we're doing in the reliability analysis is effectively trying to integrate the probability density functions in this region to determine the likelihood of failure. So if we move in, bring those general concepts into the arena of flood defense reliability, when we're thinking about levees or embankments, there's potentially a variety of different ways the structures can fail. This slide just shows an abstract from work that was done on a recently funded, EU-funded research project known as FloodSight. So this project identified about 50 or 60 potential failure mechanisms for embankments, and this is just one of them. So what we have here is a description of the failure mechanism. We have the formulation of the limit state equation, and then a description of the parameters that feed into that limit state equation. And what we're doing on FloodSight is informing these estimates of the parameters with censored data. These, on the FloodSight project, these limit state equations have been coded up into a software tool, and the software tool does reliability analysis using Monte Carlo simulations to generate fragility curves. One of the drawbacks of this type of system is that these limit state equations are relatively simple. Often we have more physically based process models that we can use to analyze failure of a structure, but typically they can be computationally more demanding. So when we try to use them in Monte Carlo simulation to do the reliability analysis, we run into problems of computational runtime. Okay, so this is just to introduce the case study for this piece of work. This is the 17th Street Canal in New Orleans. What we had here was a failure, a breach here. The loading was below the crest level of the structure, and there was consequence inundation in this area. Obviously not breaching on this side, not inundated. This shows the profile of the structure, and our colleagues at TUD developed this finite element model that was seeking to simulate these types of failure processes. The problem in this particular case is we'd like to use this type of model to do the reliability analysis to generate the fragility curve for use in the flood risk model, but the computational runtime is quite significant, and standard Monte Carlo type simulations are not really practical in terms of runtime. So one way of overcoming problems with computational runtime is to use meta models. Essentially, when we're developing a meta model, what we do is run the complex model for a range of different input parameter sets, generate the output results. We then try to fit statistical models. There's a range of different techniques we can use. And then we run the meta model in the reliability analysis as an approximator to the full model. These types of statistical models take a fraction of a second to run and are computationally very efficient. But if we want to set up a meta model for the finite element model, we've got a bit of a problem with the number of input variables to that model. So if we were to train the meta model globally over the whole parameter space, we potentially, say, select 3 different points covering the parameter space for each parameter, 10 parameters. We've got a lot of simulations to do. Again, that's not particularly practical. However, if we look at the nature of the problem, we're not really interested particularly in training the meta model well in a region that's up here. So we're not particularly bothered about understanding whether it's really safe or really, really safe, or it's completely failed or totally completely failed. So these areas here, we don't necessarily need to refine the analysis. However, along the limit state, this is where we need to train the model. Our output results are very sensitive to the performance of the meta model in this particular area along the limit state. Problem is, we don't know where the limit state is prior to doing any analysis. So the way this problem was solved was to use an optimization algorithm in conjunction with the meta model. And the optimization algorithm allowed us to train the meta model, particularly on the limit state equation, which is where we need it to perform well. So this slide just shows that process. I'll just explain a little bit about these. These are 2 of the more dominant parameters of the finite element model. Each one of these dots is a realization of the full finite element model. The dark dots indicate parameter input sets that are close to the limit state or on the limit state. So we start off with a generation of 100 samples drawn at random across the input parameter space. We then feed back the results into the optimization algorithm, which gives us a new set of parameter inputs, trying to find where the limit state is. And we repeat that process a number of times, and this slide here just shows all of those solutions combined. So what we have is a set of realizations from the full computational model that's well clustered along the limit state. We use this data set to train the meta model, so the meta model performs well along the limit state. So what we were able to do with the combination of the optimization algorithm and the meta model was to reduce the potentially 60,000 simulations down to around about 2,000 simulations. So when we train the meta model with those 2,000 simulations, we were able to obtain reliable estimates of the fragility curve when we compared to full Monte Carlo simulation done on the finite element model. Okay, so just to finish off with some conclusion. Fragility can be a very important component of flood risk analysis. Constructing meta models alone to represent the complex models can still be problematical where we have a lot of input parameters. We can refine the analysis focusing on the limit state using the optimization algorithms, and we can get significantly improved computational run times. And there's a paper that's recently been published there if anyone's interested in more details. Okay, thank you.
Okay, thank you, Ben. Questions for Ben? I know it's late. There sure must be any question.
I can always ask questions.
Yes, I know.
My question to Ben, we started the discussion some time ago. So given your activities in, trying to model the different things to train your faster analysis, so do you think it's feasible to use our simulations of the real-life dike structure to then use for predicting behavior of the other dikes? So, yeah, let's go.
So obviously the live or the Ike dike has a specific construction profile and specific soil properties, and it's unlikely that those properties or features are going to be specific to different sites. So this is very much a site-specific method. But what you can do is use the type of model that Daniela is trying to develop. And you can train site-specific models using those more complex models, and potentially reduce computational run times by putting in these meta models instead of the full models in the warning systems.
Okay, Eric.
You mentioned going through about 50 or 60 different failure mechanisms and describing those. I think the one you showed was something like a macro stability model. I know there's a lot of work done here in Holland by the TU, by Deltaris, on building up ground mechanical models for that as well. Do your models differ from that, and are they location or soil characteristic specific, or can they be translated in an international manner?
Okay, so in that report where we have 50 or 60, those failure mechanisms were identified by people from all of the flood site partners. So that included people at TUD, Deltaris, and many other places. So, but one of the criteria there was, I mean, they're all generic for specific structures, but they're all relatively simple formulation. Typically, they're well-used empirical formulae, but they contain, in some cases, quite a lot of simplifications. So these can be used widely at different sites, but you need to be aware of the potential uncertainties due to the simplifications in the limit state formulations. And certainly there's a whole range of different model types that simulate the physical processes better than those simple empirical formulations.
Okay, other questions? If not,